talking about just the alkanes, I believe. We were talking about the CH. Did we get to the alkenes?
No.
No. Okay, so we're just talking about
The last thing we talked about was concerted rocking.
concerted rocking. Because we were talking about the CH group. So we finished up on that carbon-hydrogen bonds of just an alkane. And so we're going to talk a little bit about alkenes and alkynes. Most of this you have already seen. So we'll go through that quickly because I want to get into a little bit more in-depth analysis of some of the other functional groups. So if we look at the carbon-carbon double bond for alkenes, we have a CH, and this is going to be the sp2 hybridized CH. We already know that these are going to show up above 3,000 centimeters to the minus 1. Those are going to be just barely above, so somewhere between 3,000 and 3,100 centimeters to the minus 1. So we're not looking all the way up to 32 or something like that. But just above that 3,000 line, we see these CH stretches, and that is due to the hybridization change. So now we have a 33% S character in that sp3 hybridized, which when you have more S character, it gives it a shorter bond, which makes it a stronger bond and will increase your K value. And if we increase that K value, the wave numbers are going to go up. So that is the stretch. We also want to look at the bend, and so a C double bond with a hydrogen sticking off of it is going to have a bend in the IR spectrum. Again, this is going to be in our fingerprint region, so it's only going to be useful when we have relatively simple compounds, but somewhere between 1,000 and 650 centimeters to the minus 1 for the CH bend. This is an out of plane bend, so the CH bending forward. We'll abbreviate that as out of plane, OOP. If we look at the spectrum that's on here, we've got our sp2 hybridized CH, our sp3 hybridized CHs, and these are both stretches. Then our out of plane bend down here is going to be in the alkene region, or sorry, the lower region here. There's two of them. This is the CH out of plane bend. And the substitution pattern of an alkene can be determined by the number of peaks and the locations of those peaks. Your book has a table of all of those and how they correlate. And so you can pair that up with here. But that's the type of thing that you really have to have a table to do. I don't expect you to memorize the entire table of all the outer plane bends for that. On the middle rest of the spectrum, all we have is the carbon-carbon double bond, around 1,500, and that is the carbon-carbon double bond stretch. Typically, those are going to show up between about 1,650, 1,500 centimeters to the minus 1. And 16. Alkyl groups on that. If you put more methyl groups on there, it's going to increase the wave numbers but decrease the intensity. So as you look at a more substituted double bond, we've seen this, the intensity of it goes down because it's more symmetrical and the dipole moment's not quite as strong and you don't see it as well, but it does increase the frequency a little bit. A couple recurring themes we're going to have today is the effect of conjugation and strain on a stretching frequency. So for conjugation, if you have a diene that is conjugated, you could draw a resonance form with a separation in charge. We put a positive charge on one end of the diene and a negative charge on the other end, and you get the alkene in the middle. If we look at the C-C bond here, that means that we are lengthening the C-C bond, and that's going to decrease the force constant. We lengthen it because it's going to have more single bond character. So if it's a partial or a double bond in this resonance form, but in this resonance form it's a single bond, and so you get a little bit more of a partial bond. It's not quite a single, it's not quite a double, it's somewhere in between. This means that your force constant is going to go down, which means that your wave numbers are going to go down as well. So conjugation is always going to lower the double bond, or the stretching frequency of the double bond. The other thing is strain. So we're going to look at the effect of strain on our different functional groups. This is a acyclic molecule, so there's no strain on that double bond. It shows up right around 1500. That one's about 1500. We have strain in it. The more strain you have, the lower. It depends on the type of structure you have. So if you have a double bond within the ring, this is called endocyclic. If the double bond is in the ring, then the more strain you have in it, the lower the stretching frequency. The six-membered ring, if you remember from OChem, is not strained. But if we go to a smaller ring, you're going to start straining that double bond because it has to try and fit into the size or the bond angle inside the ring. So we go from 1646 for your standard stretching to 1611 for the one inside the ring. So that lowers it slightly, about by 30, but it's not entirely consistent. Exocyclic, meaning it's outside of the ring. I don't have any examples here, or I don't have the numbers. But the double bond is attached to the ring, but it goes outside of the ring. Then as the strain increases, the wave numbers are going to increase. And you will get a stretching frequency that is at higher values.
I'm confused why if the strain increases, why the wave number decreases. I'm sorry, I didn't catch that.
So in this case, the strain is going to be pulling the bonds closer to it, and that has to, it changes the double bond character. Because in double bond, ideal alignment is to have the two carbons directly parallel with each other, and as you increase the strain on that, it's going to try and, they're not going to overlap quite as well. And so they're not going to have quite as good of an overlap in the double bond, so it's going to be a little bit less, and your stretching frequency is going to be a little bit less.
Okay.
Okay. Any other questions? Okay. What about triple bonds? Well, pretty much just very simple analysis here. We're going to look at the CH bond and then the triple bond. Pretty much exactly the same that we've seen in organic before. So in the alkynes, you have your CH stretch. Base value is about 33, yeah. Millimeters to the -1, and it's going to be a very sharp signal, as opposed to the OH signal in that region. And this only occurs if it's terminal. When you have the alkyne at the end of the chain, so you actually have a CH on the alkyne carbon. We've already seen that. And the other thing with the alkynes is the triple bond stretching frequency. That is going to be around 2150 centimeters to the -1. And again, typically we're going to see these in terminal alkynes because the dipole moment is going to be different between the two carbons. If you have a internal alkyne, their stretching frequency is not, or sorry, their intensity is pretty weak. So if you have two carbons in there, these are going to be weak signals because they don't have a strong change in dipole moment and they're not very, don't absorb the light very well. That's essentially all we have to look at here. So we have the CH stretch on our spectrum and our triple bond stretch in the 2100 range. When you're looking at these, pretty much the only things that show up near that is the nitrile. And if you see a real strong peak without the CH, then you know it's a nitrile. If you see the CH and a strong peak, then you know it's a terminal alkyne. Internal alkynes can kind of be sometimes invisible in a IR spectrum, so you might need a different form of spectroscopy to identify those. So nothing new there, hopefully, no new surprises. Okay. Aromatics. We have some new stuff here. So we have the CH. Just like before, you just like with the alkenes, you have an sp2 hybridized CH, so they're going to show up in the aromatic, or the above 300, 3000, whatever number that is. Let's start editing this. Same CHs because they are sp2 hybridized, so they're going to show up above 3000. And then we want to look at the C, double bond C, in an aromatic structure. There are lots of possibilities for the different stretches here, and they tend to show up in pairs around 1600 and 1450 millimeters to the -1. And depending on substitution patterns around the ring and what is attached, you're going to show more than just, typically more than just one. You usually see two at least. So if we look at this spectrum, we have our sp2 hybridized CHs, we have sp3 hybridized CHs, both of these being stretches. And then we have two signals here, three signals really in this region, that are going to be related to our aromatic C double bond C stretches. Within this region, we also saw the CH bending. You remember we had a CH bend right around 1450, so one of those is also the CH bending. Probably, I'm not sure which of these two, to be honest. That's the CH3 bend. So those three, we can assign those. The stretching frequency of these alkenes is a little bit lower because they're all in conjugation. And so they are entirely in conjugation. Remember, we can draw the resonance form here. With the double bonds all moved around. So essentially these are about 1.5. So they're a little lower than your standard alkene stretching frequency. The next part we want to look at is the CH bending. There's a nice table in your book and a chart, so I'll refer you to that. But essentially, you can look at a certain region of the IR spectrum to tell you about what the substitution pattern is on your aromatic ring. This depends on how complicated your fingerprint region is. If it gets too complicated, then you can't really identify it. So it's your CH of the aromatic ring here, bend, and this is an out-of-plane bend. And it's ranging from about 600 to 1,000 in the different numbers we're looking at. Then they also have an overtone between about 1667 and 2000. When you're analyzing these, be careful because there are lots of peaks that show up in those regions, and it depends on the type of functional groups that are attached to the aromatic ring. So within the reliable category, we have alkyl, alkoxy, so if you have an RO group on there, an acyl, so a ketone attached to the ring, halo, so some type of halogen, or amino. Those are attached to the ring, then the out-of-plane bending is going to be more reliable. Not reliable or unreliable would be the NO2 group, the ester, amide, and the acid chloride. On this one, we have an alkyl group attached to the aromatic ring, so this would be considered a reliable one. This can tell us, if we look at the bands here, we have two signals here in the region that's 600 to 1,000, and then we have this pattern here in our overtone of the CH aromatic region. Those two, if you match them up with the chart, correspond to a mono-substituted aromatic ring. I have several more examples of these with different substitution patterns, so we'll look at those on the next couple slides. I'm just going to skip. This slide is the paraxylene, which was the full spectrum, but if you go to the slide after it, that's actually on this next slide, so we'll just do the straight comparison of all four of them together. So the paraxylene is this one right here. So there's your para substituted. This one on your bottom right is the toluene from the first, and then we have a meta substituted and ortho and meta substitution patterns. So if you look at the double bond region, we see that they each have the aromatic CC double bond pairs, so we have 1500 and about 1400 there. We see the two there, two there, two here. And then if we look at the specific ones within the 600 to 1000 region, we see either one or two in these regions, and sometimes they have three. Actually, one of these is more than that. Yeah, that little tiny guy counts for something. And it depends on where they are. So we have a 700, about an 800, and a 900 in this one. Here we have a little bit below 700, a little bit above. This one's right at 800, and then we have one closer to 700 in the ortho substituted. And again, you can use your book to correspond to these substitution patterns. The overtones of these are shown in this 2000 to 1600 range here. And they have a blow up of those. The more reliable of these two is actually the regular peak, not the overtone. But these can sometimes get shuffled in with a lot of other things that absorb in this region, so it can be rather complex to interpret. Yeah, you gotta be careful with these. Sheldon?
What's the best way to tell between the toluene and the meta substitute? Because they look really similar, and then and when you're working with IR, how would you tell the difference without making a mistake?
Without making a mistake? That's a good question. Nice caveat at the end there. You want to try and match up those patterns as close as possible. There may or may not be that extra peak around 900, but that can be shifted. See, there's not much, or that could be covered up by other things. There's not much of that in the mono substituted. Yeah, you're right, these patterns here can be very close and difficult to interpret. So you have to do your best, and maybe you can only narrow it down to two options. Maybe you can rule out the para and the ortho, but you can't quite narrow it down completely.
Okay, and then does it, after that, would it just come down to like maybe if you have the molecular formula working with it?
No. Well, on this one, yes, but let's say we had an ethyl group here. So it ended up being a mono substitute with the same molecular formula, that you wouldn't be able to tell directly. You would have to probably use some other type of spectroscopy to determine that. So you can narrow it down, but you may not be able to do the final assessment unless you can do a direct comparison to the actual spectrum. Other questions?
So on a test, would you want us to like rationalize why we think it was a meta substitution, or would you not ask us that?
I'm not going to ask that on the test.
Okay.
So you're not going to have that table in front of you, and I don't expect you to memorize it.
Okay.
Besides, you just had to do it on a worksheet. Right? Or problem set or whatever I'm calling them. CN or triple bond here is going to be just the one peak we're looking at, so look for that band right at 2200, 2250. Based on the trends we've seen already, if that was conjugated to something, what's going to happen to the stretching frequency?
Lowers it?
Up or down?
Down.
Down. So, conjugated is going to take the stretching frequency and push it down. In this one, our peak is at 2230. And that's down from the 2250 that you're looking at, and that's because it is conjugated with the aromatic ring. So you can see this is a conjugated system, and it's going to shift that value. At this point, we need to be more specific about our values, and knowing that 2250 is the nitrile, then what's happened? We're not at 2250. How has it shifted a little bit? And we're going to look at this in a lot more detail on the carbonyls, but you need to be looking at nitriles, alkenes, and carbonyl stretches in particular, and knowing exactly where they're supposed to be and why they're not there. What else is happening within the molecule to change that? CHs, things like that, you're not going to be interpreting exactly what's going on in the molecule based on those. But these distinctive peaks, the nitrile, the alkenes, and the carbonyls, you're going to want to know more specific values and be able to interpret those in much more detail. This also has the monosubstituted and the aromatic stretching peaks here. We have that overtone. Now notice that this one has 3 peaks in this region, even though the monosubstituted is only supposed to have 2. So we've got other things going on in the molecule, and that's why this interpretation gets a little bit fuzzy. You want to be very careful with them. Also, that's not one of the ones that's said to be reliable on. It's actually not on our list, on either one. But I'm not sure how reliable it would be on this functional group. Carbonyls. This is probably the most important portion of the IR spectrum, because your carbonyl peak is always going to be there, and it's very dependent on the type of carbonyl it is, what type of functional group it is, and where it's located. These base values, I expect you to know. So an anhydride is going to have 2 bands, 1760 and 1810. Your acid chloride is 1800. Ester, 1735, aldehyde, 1725, ketone, 1715, carboxylic acid, 1710, and the amide at 1690. Those base values you should know. What these base values are is for the simplest case of a ketone, without any additive effects, it's going to be at 1750. And that's actually pretty reliable within a couple wave numbers. If you're thinking you have a ketone, but it's showing up at 1750, it's either not a ketone, or something else is happening to shift it based on conjugation, well, not that direction, but some type of strain or inductive effects to raise that stretching frequency. You need to know your functional groups in order to kind of assess what's happening within each of these and what's changing them for their base values. So for a ketone, we're at 1715, but then when you look at an ester, an anhydride, or an acid chloride, all of those are a little bit higher. That is because when you change from a ketone to an ester, or one of the other functional groups, we've added an electron withdrawing group. this electron withdrawing group is going to pull electron density away from the carbon-oxygen double bond, and that's going to shorten the bond of the double bond. So we're pulling that electron density away from it, and that's going to shorten the C double bond O, which is going to increase your force constant and increase your wave numbers. So electron withdrawing groups directly attached to the carbonyl are going to raise it. So we go from 1715 to 1735 for the ester. The anhydride has another oxygen. The acid chloride has a chlorine attached to it, so it's even more electron withdrawing. The amide, though, is all the way down at 1690. That's because even though the amide has a nitrogen attached to it, it's not quite as electron withdrawing. So even though there's a slight electron withdrawing, there is a strong contributor to resonance. Where we put a positive charge on the nitrogen and a negative charge on the oxygen. And you get a partial single bond character. And partial double bond character, and that resonance is going to decrease that K value and decrease the stretching frequency. The ester has that, but it's to a lesser effect because oxygen really doesn't want that positive charge. Nitrogen doesn't care as much. You can take a positive charge. And so the amide gets shifted down by resonance, whereas the ester and the acid chlorides and the anhydrides are all shifted up by electron withdrawing groups. And the carboxylic acid is also shifted down because hydrogen bonding. So remember I told you that hydrogen bonding caused the carbon-oxygen bond, or yeah, the oxygen-hydrogen bond to shift down. Now we're looking at the carbonyl of the acid, and it is also shifted down due to hydrogen bonding. You remember that was the dimer that could form. And hydrogen bonding decreases the wave numbers. We have this difference in between the different types of carboxylic acid derivatives we have, but then you can also have the same type of effects within a class of them. So let's say we had a ketone, and one ketone had strain, and the other one didn't. That's going to affect its stretching frequency as well. So that was the effects within the different, or between functional groups. Now we're going to look at within one functional group, and how is that base value going to change higher or lower. And two things that raise the CO frequency, one of them is strain, just like with the alkenes. So if we had an alkene that's exocyclic, it's going to increase the stretching frequency. Carbonyls are always exocyclic because the oxygen is always outside of the ring, and so this is exocyclic. And it's going to increase when you get a smaller ring. So this standard cyclohexanone 6-membered ring is not very strained. has a stretching frequency of 1715. When we go to the cyclopentane, to a smaller ring, you go up to 1745. So it's going to increase the stretching frequency. Smaller ring increases the stretching frequency, and it's typically by about 30 centimeters to the minus 1 per carbon you take away. So you take away one carbon, we go up about 30. If we took away another carbon, made it a 4-membered ring, we're going to get even higher. And your book lists out all those different stretching frequencies. The other thing that can raise the stretching frequency is electron withdrawing groups. So now we're not talking about electron withdrawing groups that are directly attached to the carbonyl, but we're looking one carbon away. Here we have an X group that's on the alpha carbon of that carbonyl, and it has a dipole moment. And so this is an electron withdrawing group. And if you add an electron withdrawing group, that is going to increase the stretching frequency. It's going to do the same thing it does with the ester, where you pull electron density away from the carbonyl, and it's going to make that carbon-oxygen bond a little bit smaller or shorter, and then the stretching frequency goes up. So those two, strain and induction with electron withdrawing groups, is going to increase your stretching frequency. Kinsey?
What about if you have larger rings, like 7, 8, 9 members?
They actually don't affect it too much because they get a little bit more floppy, and they can release any tension by just flopping around a little bit. Your 5-membered ring is stuck.
Yeah.
It can't release that tension very well in any way it goes, like shards. So the larger rings don't affect it too much. These two raise it, the next two lower it. These are essentially what we've seen already, but as a review, if you have resonance, it's going to increase or decrease the stretching frequency. And so if we go from a standard ketone to this conjugated ketone, now we have a ketone and the double bond there. And we can draw the resonance form where we put the negative charge on the oxygen, positive charge out here on the carbon. This is a very common resonance form. And it's going to, again, lower the stretching, or the force constant, which lowers the stretching frequency. And this can be by anywhere from 25 to 45 centimeters to the minus 1. When you have this kind of setup, you may also see two different bands, because you can have what we call a S-cis conformation and a S-trans conformation. And you may see signals from both of these showing up within the molecule. Now this is only if they are not in a ring system, because if they're in a ring system, they're going to be stuck in the S-cis conformation. No, sorry, said that wrong. The S-trans conformation. But if it is acyclic, they can flip over, and you may see more than one band in that region, because you're seeing the two different conformations in ions. You gotta be careful when you're interpreting those. Finally, if there's any hydrogen bonding, that's going to decrease the stretching frequency, and you'll end up with a slightly lower frequency. So if we were looking at a ketone that had another alcohol somewhere in the molecule, instead of 1715, you may end up at 1710 or 1700, but it's still a ketone. just has hydrogen bonding. So we've got to look at the actual numbers on the spectrum now, not just, oh, it's in the 1700 region, it's a ketone. You need to analyze it further now. I have a couple of examples of spectra on the next slide. Any questions?
Is there ever a time when a peak is like displaced more than like 100 centimeters? Like, would that be abnormal?
They're pretty unusual structures, but it does happen. So if you look in your book, they go from like the cyclohexane, hexanone to the 4-membered ring. It's nearly a 60 or 70 centimeter wave number jump because of that. And so it can shift significantly. And maybe there's additive effects. Maybe it's a smaller ring and it has a double bond or something. Then it can be additive.
Why is this the opposite effect of induction? Or it seems like it is in some ways like an electron drawing group.
Which one? The hydrogen
The
bonding?
hydrogen bonding, yeah.
Because you are donating some of this electron density towards that hydrogen. And if we donate that hydrogen density, it's going to give us a little bit more of a single bond character. So it weakens that bond a little bit. It's going to give us a partial positive charge over here when we do that. So it does make it a little bit more like a single bond because you're donating some of that bond character.
As opposed to an electron withdrawing group, which...
If the electron withdrawing group is over here, it's going to pull the electron density towards itself. We're pulling it in. We're pulling that oxygen in rather than out. The simplistic way of stating that. When you're looking at these, you don't have to go just on, if you're looking at functional groups, you don't have to go just on the base values. You also want to look at what's within that structure of that derivative and pair it with other stretches in the IR. So if we're looking at an anhydride, well, I should state that the anhydride, yeah, that's my next example. No, 2 examples. All right, I'll get to the anhydride. But let's say we look at this one and we see the stretching frequency is at 1658 for our strongest one. It's a little bit low for the carbonyl region, but it is an amide. And the amides, 1690 is kind of our base value. This is shifted a little bit more, probably by hydrogen bonding within or between different amide molecules. And we see that when you look at the NH or OH region, we see 2 peaks within that. So that can lean us towards having an amide. So you want to look for, okay, I've got a carbonyl, but what functional groups have carbonyls? There's lots of them. It's not just a ketone. So an amide, we're going to look for NH2 groups. A carboxylic acid, we're going to look for the OH peak. An ester, we're going to look for a CO bond. The anhydride will look for 2 peaks in the carbonyls because there's 2, and they can do symmetric or asymmetric stretching. Aldehyde, you look for the CH of an aldehyde. Am I missing any? Acid chloride. You hope you can see the Cl. But you also look at where it is in the spectrum. So if we look at this anhydride, we see that there are 2 strong peaks in our region, 1726 and 1788. And this goes to the C double bond O stretch. And this is going to be the asymmetric stretch as the higher one. Typically asymmetric is higher. And then we have the C double bond O for the anhydride that is symmetric. So we see 2 stretches, one for the asymmetric C double bond O stretches and one for the symmetric one. These are shifted a little bit down from what the base values were though, because it was 1810 and 1760. This is 1780 and 1720, but it's because they're conjugated. They have an aromatic ring on either side here and this is a conjugated carbonyl. So even though you see the anhydride there, you have to be careful with the base or the values we're looking at. They're conjugated, so just sit down. And you see the aromatic peaks in there, in here. And we also see the CO bond. Well, this is where we'll have to just talk about the CO bond. That's the last important one. The rest are rather unimportant comparatively. So our CO bond is going to be within the region of 1300 to 1100 centimeters to -1. And these are going to be pretty broad, and they're going to be pretty strong peaks. Whereas most of the peaks in the fingerprint region can be a little weaker, or pretty narrow. Our C double bond O stretch, or C single bond O stretches are going to be weaker. Here and here, or not weaker. They're strong and they're broad. In this one we have a asymmetric and a symmetric stretch. In general, for your anhydrides, we're going to see both of those, and for alkyl ethers and things like that, we may only see one. So if you see a nice broad stretch like this, between 10,000 and 13, you're seeing the CO single bond stretch. Yeah, that's essentially the nutshell of what we're going to cover on the last few slides. So we will stop there because I need a little bit of time for the writing into